Usually when we talk about a medical diagnosis, there is this very strict expectation of precision. I mean, it feels almost like engineering, right?
Oh, absolutely.
Mm.
You break your arm, the x-ray shows that jagged white line across the radius,
Yeah.
and the doctor just, points at the screen.
Yeah, they just point and say, there it is.
Right. It's binary.
Right.
The bone is broken, or it isn't. And I think as humans, we are incredibly comforted by that.
Mm-hmm.
We want our problems to be visible, neatly categorized, and easily solvable.
But the moment you step out of that single patient room and look at the world of healthcare informatics, like when you try to diagnose the health of an entire hospital system using thousands of data points, that X-ray machine just shatters.
It completely shatters.
Yeah, we are suddenly operating in a diagnostic landscape that is, frankly, incredibly murky. We are trying to turn massive, chaotic piles of raw data into actual insight and action.
Which is not an easy task.
Yeah, no, not at all. So whether you are a healthcare leader trying to track patient outcomes across a 100-bed hospital, or you're just, looking at a sprawling spreadsheet at work and trying not to feel completely overwhelmed, the tools of data literacy are what separate clarity from total institutional collapse.
And we really have to start by completely reframing how we view those spreadsheets.
Mm-hmm.
Data isn't just cold numbers on a page.
Right.
It isn't just arithmetic. It is fundamentally about storytelling. And in healthcare specifically, the numbers we collect are a profound extension of human care. They are basically the mechanism we use to listen to the system at scale.
Which brings us to the very first trap we have to avoid on this deep dive. Because if we want to listen to the system, we have to understand what we are actually hearing. People constantly use the words data and information as if they're the exact same thing.
Oh, all the time.
But they are entirely different operational concepts. Today we're looking at transcripts from a data analysis and Excel course, paired with chapters 10 and 11 from a nursing leadership textbook by Waxman, focusing on healthcare informatics. And they make this distinction very clear.
They absolutely do. Data, in its rawest form, is just uncategorized, unorganized facts.
Just raw stuff.
Exactly. It's individual figures, isolated numbers, or even unstructured opinions and feelings. It is just the raw input. And the defining characteristic of this raw data is that it often exists without any adequate validity or reliability checks. It is literally just a massive reservoir of unfiltered inputs sitting in a server.
Right, so then information is what happens when you impose order on that chaos?
Yes.
Information is data that has been organized, categorized into useful groupings, and most importantly, subjected to intense critical analysis. It is data that has been actively connected to a real-world issue to inform decision-making.
That connection is key. You take the data, you structure it, and it becomes information. Then you apply human intuition to that information, and it becomes insight.
But the entire pipeline from data to insight is remarkably fragile, isn't it?
Oh, incredibly fragile. It relies on a principle that originated in the early days of computer science, but it applies to every single modern dashboard. GI Go.
Garbage in, garbage out.
Garbage in, garbage out. If the raw data you are feeding into your system is flawed, it really does not matter how sophisticated your analytics software is or how beautifully designed your predictive dashboards are.
The output will be garbage.
Total garbage. So to prevent that, you have to lock down two critical concepts before a single calculation is made: reliability and validity.
Okay, let's unpack this, starting with reliability, because this is essentially about consistency and dependability, right?
Exactly.
If a measurement is reliable, it means that if you repeatedly measure the exact same phenomenon, you will get a similar result every single time.
Precisely. It's about the stability of your collection method. But, in large organizations, reliability often breaks down not because of malicious manipulation, but because of localized rational decision-making that just corrupts the systemic data.
Wait, what does that look like in practice?
Well, consider a hospital administrator trying to determine the financial cost of clinical preceptorships. They need to know exactly how much time and resources it costs to train nursing students on the floor.
Right, for the budget.
Right. So to build that budget, they need data on how many students are actively working on the units.
So they go and look at the staffing plans.
Yep. And on one inpatient adult unit, the staff meticulously and compliantly list the exact number of student nurses per shift directly on their official documentation.
Perfect. High reliability there.
But on another unit, the staff handles it completely differently. They have a full roster of students, which requires a massive amount of time from the staff nurse preceptors. But to make their documented workload accurately reflect how hard they are working, they creatively, let's call it, adjust the recorded regular staffing hours.
Oh, wow. So they essentially hide the presence of the students within the math of the regular staff hours.
Exactly. Now, they aren't trying to destroy the hospital's budget. They are just trying to survive their shift and get credit for the work they are actually doing.
But the systemic consequence is catastrophic for the data.
It completely destroys the reliability of the data set. Because there is no standardized, rigidly enforced system being used across both units to document the presence of students, the aggregate financial data pulled from those staffing plans is fundamentally flawed.
So if the chief financial officer uses that data to allocate funding for the preceptorship program next year, their projections will be entirely wrong.
Completely wrong. The data collection was not consistent, so the output is garbage.
Right. Okay, so that's a mechanical failure of consistency. But validity, from what the textbook describes, seems far more insidious. If reliability asks, are we measuring consistently? Validity asks, are we actually measuring the concept we think we are measuring?
Yes. Validity failures are the silent killers of strategic initiatives. Because here's the thing. You could have incredibly reliable data collected perfectly, consistently every single day that is completely invalid.
Is it actually possible for data to be highly reliable but completely invalid?
Oh, it happens all the time. The classic example of this is the ubiquitous patient satisfaction survey.
Oh, right.
We assume that because a survey is printed on official letterhead and tabulated by a computer, it is generating valid data about how happy patients are.
But it's not.
Not always. There was a 1996 British study that exposes this perfectly. Researchers took 3 different forms of patient surveys and distributed them. Now, the clinical care the patients received was identical,
Okay.
but they found that simply changing the phrasing of the questions completely altered the satisfaction scores.
Just the phrasing.
Just the words on the page. If they asked patients if they agreed with a negative description of their hospital experience, the tabulated data showed higher apparent satisfaction than if they asked if they agreed with a positive description.
Wait, really? The actual clinical experiences did not change at all?
Not at all. Only the words on the paper changed, which means the survey was not actually measuring patient satisfaction. It was measuring the psychological reaction to the phrasing of the questionnaire.
So the instrument lacked validity.
Exactly. A more recent example reinforcing this is a massive 2011 study of over 8,000 German patients. The researchers wanted to know what actually drives a patient's overall satisfaction score.
And what did they find?
They found that the objective treatment outcome was the strongest predictor, closely followed by the perceived kindness of the nursing staff.
That makes total sense. But hospitals spend millions of dollars generating informational pamphlets, creating complex educational videos, and, ensuring patients receive massive binders of information about their treatment.
Oh, they track the distribution of these materials religiously.
Right, and that German study found that survey items regarding satisfaction with the amount of information the patient received had almost no significant influence on their overall global satisfaction score.
None. So if a hospital leadership team decides to boost their lagging satisfaction scores by pouring their budget into a massive informational pamphlet program, they will fail.
Because they're tracking a highly reliable metric, the number of pamphlets distributed, but that metric is completely invalid for predicting overall patient satisfaction.
Exactly.
I mean, my analogy for this is, it's like trying to measure your body weight using a tape measure.
That's a great way to put it.
You can wrap that tape measure around your waist every single morning. It will give you a highly reliable, consistent measurement of your circumference. But if you are using that number to track how many pounds you weigh, the data is entirely invalid. It is just the wrong tool for the fundamental question.
And the most profound example of a validity failure in the research centers on emergency department, frequent users who present with pain complaints.
Oh, this was fascinating in the text.
Right. There is a deeply entrenched assumption in medicine that a patient seeking pain relief will only report high satisfaction with their care if they walk out the door with the prescription for a scheduled narcotic.
That is the operational assumption driving countless triage policies right now.
But the 2017 ED opioid study completely inverted that narrative. The data revealed that for these frequent ED users, their satisfaction with the clinical staff was not driven by the receipt of opioids.
What was it driven by then?
It was primarily driven by compassionate treatment.
Oh.
It was driven by a distinct feeling that they mattered to the staff, their perception that safety precautions were being strictly followed, and their wait time. The actual receipt of a scheduled drug prescription did not significantly influence their reported satisfaction with the nurses or physicians.
Think about the systemic implications of that. If a hospital administration operates under the invalid assumption that drug-seeking behavior dictates satisfaction, they might pressure physicians to overprescribe just to keep the metrics up.
Exactly.
By failing to understand validity, they aren't just making a mathematical error. They are potentially fueling an opioid crisis and completely ignoring the actual drivers of patient care, which are compassion and safety.
This is exactly why you have to interrogate your data before you ever open a spreadsheet. You have to ensure the data is both a reliable scale and a valid measurement of the clinical reality.
Right. And once you have secured that foundation, you face the next hurdle, which is organization. Because you cannot analyze what you cannot mathematically define, you have to understand the specific architecture of your data set.
Yes. If we look at the transcripts from the Excel analysis course, they break down the fundamental anatomy of a data set into variables and observations.
It seems basic, but misinterpreting this grid is where complex analytics projects die in their infancy.
Oh, completely. When you look at a standard data set, let's use the top 20 cars data set from the course, tracking 2010 and 2011 sales. You're looking at a two-dimensional grid. The columns are your variables.
Right, so a variable is simply the characteristic or the quality of interest you are measuring.
Exactly. Column A is the rank, column B is the manufacturer, column C is 2010 sales. Each column is a distinct attribute.
And the rows are the observations. An observation is the specific instance or entity that holds the values for those variables. So row 2 contains everything about the Honda Accord. Row 3 contains everything about the Toyota Camry.
Yes, and if we shift this to a hospital setting, the variables in your columns are the disease symptoms, the admitting diagnoses, the lab results, and every single row represents an individual patient's specific journey.
But here is where we hit a critical constraint. Not all variables are created equal, and your data type dictates your mathematical reality.
What's fascinating here is that the specific level of measurement you use to collect a variable restricts entirely what statistical techniques you are allowed to apply to it later. If you misunderstand this hierarchy, you will generate phantom statistics.
Okay, let's start at the absolute bottom of the hierarchy then, nominal data.
Yes.
Nominal essentially means name and only. These are arbitrary classifications into mutually exclusive categories, like gender, ethnicity, religion, or a patient's room number.
The danger with nominal data is that software systems require you to code these categories into numbers to process them. You might code female as 1, male is 2, and non-binary is 3.
Right.
The trap is that a computer sees a 1, a 2, and a 3, and it assumes it can perform arithmetic. But those numbers are just digital name tags. You cannot add 1 and 2 to get an average gender.
Right, or you cannot calculate the average room number on a surgical floor to find out where the average patient is located. The numbers hold absolutely no mathematical weight.
Moving one step up, we have ordinal data. This introduces the concept of ranking. The classic clinical example is the 1 to 4 pain scale. 1 is no pain, 2 is slight, 3 is moderate, 4 is significant.
So ordinal data tells us the direction of the relationship. We know definitively that a patient reporting a 4 is in more distress than a patient reporting a 3.
Exactly. But ordinal data lacks equidistant intervals. We do not know exactly how much worse the 4 is compared to the 3.
Ah, I see. The subjective leap in suffering between slight pain and moderate pain might be vastly different than the leap between moderate and significant pain.
Because the space between the numbers isn't uniform, applying advanced predictive modeling to ordinal data can heavily skew your results.
Which brings us to the gold standard for statistical analysis, right? Interval and ratio data. This is where the distance between every single number is mathematically identical.
Yes. Interval data is ordered, equidistant, but it lacks a true 0 point. Temperature in Celsius is the classic example. 0 degrees does not mean the absolute absence of molecular heat. It's just an arbitrary point on the scale.
And ratio data.
Ratio data is the pinnacle. It is ordered, equidistant, and it possesses a true, non-arbitrary 0. Blood pressure, length of stay in hours, or financial cost. $0 means an absolute absence of money.
Right, that makes sense.
In practical, everyday statistics, interval and ratio data are treated similarly. These are the domains where you can deploy your heavy mathematical artillery.
There is also a vital distinction to be made between continuous and discrete data within those higher levels, isn't there?
Yes, absolutely.
Continuous data asks the question, how much? It can be fractured into an infinite number of decimal points, a patient's age, their exact serum potassium level, or a length of stay measured down to the millisecond.
Whereas discrete data asks how many. It is a strict whole number count. You can track the number of disease cases or the number of live births in a ward. You cannot have 2.5 births.
So why does this level of measurement matter so much before we even open Excel?
Because understanding these levels of measurement isn't just an academic exercise. It is the prerequisite for using tools like Excel without blinding yourself. The software is infinitely obedient, but it has zero clinical context.
Right.
If you feed it nominal data like a column of ZIP codes and click the average button, it will dutifully calculate a number with 4 decimal places. And that mathematically perfect number will mean absolutely nothing in the real world. You have to know the constraints of your data before you ask the machine to calculate it.
But when you do have the right data, the organizational power of these tools is immense. Like the course transcript highlights how sorting and filtering can instantly isolate the signal from the noise.
Oh, sorting is incredibly powerful.
Right. You take a massive data set of hundreds of vehicles, initially sorted by 2011 sales. By applying a custom sort based on 2010 sales, from largest to smallest, the entire architecture of the spreadsheet shifts, instantly revealing a completely different historical narrative about market dominance.
And filtering is arguably even more powerful for clinical analysis. When you are staring at a spreadsheet of 10,000 hospital admissions, you are looking at cognitive overload.
It's just a wall of numbers.
Exactly. By applying a filter to the admitting unit column and isolating only the intensive care unit, you strip away thousands of irrelevant rows. You narrow the universe of data down to exactly what you need to analyze.
So let's say we've done that. We have filtered our pristine ratio-level data. We are looking at a critical metric across thousands of patients. Even filtered, a human mind cannot comprehend 1,000 individual numbers simultaneously. We have to summarize the reality. We have to find the center of the data.
This is the realm of descriptive statistics. We need to find a single number that accurately represents the entire group. We rely on the measures of central tendency, the mean, the median, and the mode.
Okay, the mean is the arithmetic average. It is the most ubiquitous statistic in the world. You sum all the values and divide by the total number of observations.
But the mean has a catastrophic vulnerability.
Oh.
It is highly sensitive to extreme values or outliers, because the mean calculates its value by pulling the actual mathematical weight of every single data point. A single massive outlier can drag the mean completely away from the reality of the majority.
Right. The clinical data set regarding adolescent patients with type 2 diabetes perfectly illustrates this distortion. Let's look at that. You have a small cohort of 6 patients. You are tracking their serum glucose levels. Patient 1 is at 125. Patient 2 is 132. Patient 3 is 124. Patient 5 is 130. Patient 6 is 120.
So the data is clustering tightly. Everyone is sitting in the 120s and low 130s. It's a very consistent clinical picture.
But then you look at patient number 4. Their serum glucose level spikes to 180.
That 180 is a massive outlier. If an analyst indiscriminately calculates the mean for this group, the average serum glucose level calculates to 135.17.
Wait, if you report to the attending physician that the average patient in this cohort has a glucose of 135, you are essentially lying with math.
You are.
5 of the 6 patients are significantly lower than 135, and 1 is radically higher. The mean of 135 represents absolutely no one in that room. It is a mathematical phantom.
Right, here's where it gets really interesting. The 180 outlier acted like a giant in a game of tug-of-war, yanking the entire center of gravity away from the actual group.
Which is precisely why the median is the analytical hero when a data set gets volatile. The median completely ignores the mathematical weight of the outlier. It simply arranges all the data points in numerical order and finds the exact physical midpoint. 50% of the scores sit above it and 50% sit below it.
In our 6-patient diabetes example, we have an even number of observations. So the median is the average of the 2 middle numbers, patient 1 at 125 and patient 5 at 130. The median is 127.5.
Compare 127.5 to the mean of 135. The median of 127.5 is a vastly truer reflection of the clinical reality for the vast majority of those patients.
It anchors the summary in reality regardless of how wildly patient 4's glucose spikes. And then for completeness, we have the mode, which is just the most frequently occurring value.
Right.
If patients stay for 2, 2, 3, 6, 8, 10, 10, 30, and 32 days, the mode is 10 simply because it appears twice. It's a useful quick glance metric, but lacks the robust summarizing power of the mean or median.
But finding the center only solves half the problem. If I tell you the median length of stay is 5 days, that doesn't tell you if everyone stays exactly 5 days, or if half the patients leave in 1 day and the other half stay for a month. We have to understand the spread, or the dispersion, of the numbers.
The most primitive measure of spread is the range. You simply subtract the smallest number in your dataset from the largest number. But relying on range for operational decisions is incredibly dangerous because it completely ignores every single data point that falls between the maximum and minimum.
The hospital length of stay example demonstrates this flawlessly. Imagine 3 different hospital units, each with 3 patients currently admitted. Unit 8 North has patients staying 2, 2, and 7 days. The range is 5. Unit 6 South has patients staying 1, 1, and 6 days. The range is 5. Unit 4 West has patients staying 10, 11, and 15 days. The range is 5.
Right, so if a hospital administrator is looking at a high-level executive dashboard, and the only metric for dispersion is range, they see a 5 across the board. They assume all 3 units are experiencing the exact same operational flow.
But the clinical reality on the floor is radically different. Unit 6 South is burning through beds, discharging patients almost immediately with one slight outlier. Unit 4 West is effectively operating as a long-term acute care facility. Their fastest discharge took a week and a half. The range masks the entire operational truth.
To actually understand the spread, we have to look at how every single data point relates to the center. We have to calculate the variance and the standard deviation. This is where the math gets incredibly elegant.
Let's walk through exactly how this works using the nursing hours per patient day, or NHPPD, across 5 different hospital units. The hours are 8.5, 7.0, 9.0, 8.2, and 5.5. The exact mean of these 5 units is 7.64 hours.
To figure out the spread, we first find the deviation for each unit. We subtract the mean of 7.64 from each individual unit's score. Unit 1 West is at 8.5, so its deviation is a positive 0.86. Unit 4 South is at 5.5, so its deviation is a negative 2.14.
Okay.
We now have a list of exactly how far every single unit deviates from the average.
But if you try to find the average of those deviations by adding them all up, you hit a mathematical wall, because the mean is the exact center of gravity. The positive deviations and the negative deviations perfectly cancel each other out. If you sum them, the answer is always exactly 0.
Right, and you can't base a metric on 0. So statisticians developed a brilliant workaround to eliminate the negative signs. They square every single deviation score. A negative multiplied by a negative becomes a positive.
Ah, clever.
You sum all those scored numbers together, and you divide by the number of data points minus 1. This final number is the variance.
But variance leaves you with a bizarre, completely uninterpretable metric. Because you squared the deviations, your resulting unit of measurement is also squared. You are left trying to explain squared nursing hours to a hospital board. It makes no physical sense.
Exactly. Variance is a mathematical stepping stone. To return the metric to a scale that human beings can actually understand and apply, you simply take the square root of the variance.
Oh, that makes sense.
That calculation brings you back to your original unit of measurement nursing hours, gives you the standard deviation.
So for those 5 nursing units, the standard deviation calculates out to 1.40 hours. This is arguably the most powerful descriptive statistic we have. It tells you that, on average, any given unit's nursing hours will deviate from the mean by about 1.4 hours. It quantifies the expected volatility of your system.
And when you pair the standard deviation with a normal distribution, the classic symmetrical bell curve where the mean, median, and mode are perfectly aligned in the center, you unlock incredible predictive power. This is governed by the empirical rule.
The transcript illustrates this with a massive midterm exam taken by 100 students. The mean score is an 80, and the standard deviation is 2.
The empirical rule dictates that in a normal distribution, approximately 68% of all your data points will always fall within exactly 1 standard deviation above and below the mean.
So you take the mean of 80. You subtract 1 standard deviation of 2, getting 78. You add 1 standard deviation of 2, getting 82. Without having to look at a single individual test paper, you know with mathematical certainty that 68 of those 100 students scored exactly between a 78 and an 82. You can instantly understand the bulk performance of the system.
The issue we face today is that software has automated all of this. In Excel, you can generate the mean, the median, the variance, and the standard deviation for 10,000 patients with a single click of the data analysis tool. The machine executes the math perfectly.
But if Excel can calculate all this in 1 click, aren't we losing our critical thinking by letting the machine do the math? If the machine instantly spits out the mean, the analyst might just copy-paste that number into a report without ever noticing the 180 glucose outlier that is completely warping the reality.
That is the greatest danger in modern informatics. The software does not know what the numbers represent. It doesn't know what glucose is, and it doesn't know what a Liesel outlier looks like.
Right, it's just processing values.
It takes human intuition to look at the raw data, spot the anomaly, and actively decide, hey, the mean is mathematically correct but clinically deceptive. I must use the median here. If you surrender that critical thinking to an algorithm, your data loses its connection to human reality.
That friction between mathematical precision and human interpretation brings us perfectly into the realm of data visualization. Because, let's be honest, numbers on a page are inherently dry.
Very dry.
If you hand a spreadsheet with 4,000 rows to a chief medical officer, their eyes will glaze over. To persuade humans to drive actual operational change, you have to visualize the data. But visualization is a double-edged sword. It can illuminate the truth, or it can be weaponized to manipulate it.
Before we get into the complex charts, it's worth noting that visualization can happen directly within the data itself. The Excel transcript walks through conditional formatting, which is a brilliant way to instantly surface anomalies without losing the raw numbers.
Yeah, instead of building a separate chart, you apply a rule to the cells themselves. You tell the software, hey, if the monthly sales percentage drops below 0, turn the text bold and the cell background bright red.
Exactly.
Instantly, across a massive grid of data, every single area of negative growth visually screams for your attention. Or you use data bars, which embeds a tiny scaled bar chart directly behind the number in the cell. A massive number gets a bar that fills the cell, a tiny number gets a sliver. It allows the human eye to intuitively weight a complex spreadsheet in seconds.
But when you extract the data from the spreadsheet to present it to an audience, you enter the discipline of data storytelling. The textbook references Dykes' framework regarding the 6 elements of a data story. It is not enough to just throw a graph on a PowerPoint slide.
You have to build a narrative architecture. You start with the data foundation, proving your numbers are reliable and valid. You establish a main point. What specific action are you asking the board to take? You develop an explanatory focus, guiding the audience away from what happened and toward why it happened. You structure a linear sequence so the logic flows naturally. You introduce dramatic elements to highlight the tension, perhaps a sudden spike in infection rates. And finally, you deploy the visual anchors, the charts themselves, to cement the narrative.
But those visual anchors are where deception frequently takes root. The textbook slide deck includes a deeply unsettling section on incorrect charts, showcasing how easily visual mechanics can be exploited to lie with perfectly accurate data.
The most egregious example is the impossible pie chart. It sounds like a joke, but these appear in professional presentations constantly. The slide shows a standard, beautifully rendered 3D pie chart divided into 4 slices, representing hospital 1, 2, 3, and 4. But when you read the labels on the slices, the percentages are 59%, 49%, 76%, and 81%. If you sum those up, you get 265%.
It is a fundamental violation of geometric logic. A pie chart, by its very mathematical definition, must represent mutually exclusive parts of a whole. The entire circle must equal exactly 100%.
So how does that even happen?
The analyst who built this chart likely took data where hospitals could overlap, maybe patients who visited multiple facilities, and forced it into a pie chart template because they liked how it looked. The resulting visual is literal nonsense. It destroys the credibility of the entire presentation.
Even more common and far more manipulative is the truncated data chart. This is the visual deception you see on evening news broadcasts and quarterly earnings reports every single day.
Oh, all the time.
The slide shows a bar chart comparing hygiene compliance across 3 disciplines: nurses, physicians, and pharmacists. The raw data is solid. Nurses are at 94%, physicians at 83%, and pharmacists at 79%.
Now, if you build that chart honestly, the axis, the vertical baseline, must start at 0. In a properly scaled chart, the visual difference between the 94% bar and the 79% bar is noticeable, but it remains proportional. You see a 15% gap.
But the slide demonstrates what happens when you truncate the axis. They chop off the bottom of the chart entirely and start the baseline at 70% instead of 0.
The visual impact is violent. Because the baseline is 70, the pharmacist's 79% bar barely registers above the line. But the nurse's 94% bar stretches to the top of the chart.
A 15% actual mathematical difference is visually rendered to look like a 500% difference.
Yes, the bar for nurses looks 5 times taller than the bar for pharmacists. If a hospital board sees that truncated chart, they might immediately launch a punitive investigation into the pharmacy department entirely based on a visual illusion created by cropping an axis.
You can also manipulate the data by stretching the axis. If you have a line graph showing a very slow, gradual increase in patient admissions over time, you can compress the horizontal x-axis and stretch the vertical y-axis. Suddenly, a gentle 2% growth trend over 5 years looks like a terrifying vertical spike. You are weaponizing the geometry of the chart to induce panic.
The textbook offers a very stark warning about this. Modern software allows anyone to generate a multicolored, exploding pie chart with continuous 3D animation in about 3 clicks.
Right. But just because we can make an exploding pie chart with continuous animation, should we?
In almost every clinical or operational scenario, a simple, cleanly formatted data table or a rigidly scaled basic bar chart is vastly superior. The moment you convert a precise number into a visual shape, you sacrifice precision for aesthetic impact. If lives or millions of dollars are on the line, you want precision.
So we have ensured our data is valid. We have organized it into the correct levels of measurement. We have calculated the central tendency while dodging the outlier traps. We have visualized it cleanly without truncating the axes. We are staring at a scatter plot and we think we see a pattern. The data points seem to be moving together. How do we mathematically prove that a relationship actually exists, rather than just seeing shapes in the clouds?
This brings us to the most analytically rigorous section of the material, measures of association. We need to quantify the relationship. The text focuses heavily on 2 specific statistical tests, and your choice depends entirely on the level of measurement of your variables. Let's look at Pearson's correlation coefficient first, commonly denoted as R.
Pearson's R is strictly reserved for interval or ratio data, the data with perfectly equal distances between the numbers. You mount one variable on the horizontal x-axis, the other on the vertical y-axis, and you look at how the coordinates plot out.
The resulting Pearson's R value is a brilliant metric because it is permanently bounded. It will always fall exactly between a -1 and a +1. A score of absolute 0 means that data points are scattered like shotgun pellets. There is absolutely no mathematical relationship whatsoever.
If the score approaches +1, you have a strong positive relationship. As variable x increases, variable y increases in lockstep. If it approaches -1, you have a strong negative relationship. As x goes up, y goes down.
The textbook provides a highly relevant nursing leadership example here. A chief nursing officer is hypothesizing that there might be a relationship between patient satisfaction scores and the number of nursing students assigned to a specific unit. Both of these are ratio data. You can count the students, and you can quantify the survey score.
The CNO plots the data across dozens of units. When the software calculates the Pearson's R, the result is a plus 0.53.
We consult the standard interpretation tables for correlation. A score between 0.0 and 0.35 is generally considered a weak or non-existent relationship, but a score between plus 0.36 and plus 0.67 indicates a moderate positive relationship. So the plus 0.53 gives the CNO mathematical proof that a verifiable relationship exists. Generally speaking, as the number of earnest, helpful nursing students on a unit increases, the patient satisfaction scores on that unit also increase.
But Pearson's R only works for numbers you can plot on a continuous scale. What happens when your data is nominal? What if you are dealing with categorical buckets like gender or blood type, or whether a patient is a smoker or a non-smoker? You can't put smoker on an XY axis because there's no numerical increment.
That is exactly where the chi-square test becomes necessary. Written as x squared, it tests for the association between 2 categorical nominal variables. The mechanics of the chi-square test are fascinating because it essentially measures the distance between reality and statistical expectation.
Let's break down the math of how it actually does that, using the textbook's example of testing whether a smoking habit is statistically independent of gender.
You start by building a 2x2 contingency table. Imagine a random sample of 100 patients. The rows are the smoking status, smoker and non-smoker. The columns are the gender, female and male. You categorize all 100 patients into those 4 intersecting boxes. This gives you your observed data, what actually exists in reality.
Okay, so let's say you look at the observed data and notice there seem to be far more female smokers than male smokers in your sample.
But your brain is wired to find patterns, even when they don't exist. You need to know if that difference is mathematically real or just a random fluke in this specific sample of 100 people.
Right, so to find out, you have to calculate the expected data.
Yes. The expected data is what those 4 boxes would look like if gender and smoking were completely 100% unrelated. You calculate this for each box by multiplying the total number of people in that row by the total number of people in that column and dividing by the grand total of 100.
So you now have a table of observed reality and a table of expected, perfectly independent numbers.
Exactly. The chi-square formula simply asks how far apart are these 2 tables. For each of the 4 boxes, you subtract the expected number from the observed number. You square that result to get rid of negative signs, just like we did with variance. Then you divide it by the expected number. You sum up the results from all 4 boxes, and you have your chi-square statistic.
In the textbook's example, after running that math, the calculated chi-square statistic is 28.56. But 28.56 doesn't mean anything in a vacuum. You have to compare it to a critical threshold.
This is where degrees of freedom comes in. It represents how many values in your calculation are free to vary. For a basic 2 by 2 table, the degree of freedom is 1. You take that degree of freedom, you look at a standardized statistical distribution table, and it tells you that the critical threshold for significance is 3.841.
Meaning, if your calculated statistic is larger than 3.841, the discrepancy between your observed reality and the expected baseline is so large that it could not have happened by random chance.
Exactly. Because their calculated statistic of 28.56 is wildly higher than the critical value of 3.841, they can confidently declare that gender and smoking status are not independent in this population. There is a mathematically significant association between them.
Okay, let me challenge you on this because this is where executives often make massive strategic errors. Let's go back to the chief nursing officer. They have that Pearson correlation of plus 0.53, proving a moderate positive relationship between nursing students and patient satisfaction. If I am that CNO, can I take that scatter plot into the boardroom, slam it on the CFO's desk, and demand a massive budget increase to double the student program, claiming that adding students will directly cause satisfaction scores to rise?
That is the single most dangerous trap in all of data analytics. The phantom pattern problem, confusing correlation with causation. A Pearson's R of plus 0.53 absolutely, unequivocally does not prove that the nursing students caused the patients to be happier.
Why not? I mean, the math proves they are moving together.
The math proves they are moving together in time and space, but it offers zero proof regarding the mechanism linking them. In any complex system, there are hidden factors, what statisticians call confounding variables that the math cannot see. Consider the operational reality of a hospital. Which units are most likely to accept the burden of training nursing students? It is almost always the units with the most experienced, highly supportive, and stable charge nurses.
Right, because chaotic, understaffed units refuse to take students.
Exactly. So it is highly probable that the exceptional leadership of those charge nurses is the actual causal variable driving the high patient satisfaction. The nursing students are simply being placed on those units to benefit from that same excellent environment.
Ah, I see.
The students and the high scores are correlated because they share a common hidden root, not because one causes the other. If the CNO forces students onto a chaotic, poorly managed unit expecting scores to rise, they will likely see satisfaction plummet as the overwhelmed staff fractures under the added stress. The math proved the connection. Human intuition is required to investigate the causality.
That distinction highlights why the concept of significance is so deeply misunderstood. We hear the phrase statistically significant thrown around in media and corporate reports as if it is the ultimate, undeniable truth. But the text explicitly breaks significance down into 3 completely distinct tiers.
Yes. If we connect this to the bigger picture, statistical significance is merely the baseline. It is step 1. It is usually represented by the p-value. P-value answers one incredibly narrow mathematical question: do this result happen by random chance?
Okay.
If you have a very small p-value, typically less than 0.05, means there is less than a 5% probability that the association you are seeing is just a random fluke of the data set.
But a p-value tells you absolutely nothing about how important the result is. It doesn't tell you the magnitude of the difference.
And that is where practical significance becomes vital. Practical significance asks, how big is the actual difference in the real world? We measure this using effect size metrics, most commonly Cohen's d, which calculates the difference between 2 groups in standard deviation units.
Okay, give me an example of that.
You could run a massive clinical trial on a new blood pressure medication involving 100,000 patients. The p-value might be incredibly small, proving mathematically that the drug genuinely lowers blood pressure. It is statistically significant.
But when you calculate the practical significance, the Cohen's d reveals that the drug only lowers blood pressure by an average of 0.2 millimeters of mercury.
Exactly. The mathematical effect is real. It wasn't a fluke. But the practical magnitude of that effect is microscopic. It is functionally useless to the patient.
Which brings us to the final and, frankly, the most profound tier, clinical significance.
Clinical significance is the point where the mathematics ends and the human begins. It cannot be calculated by an algorithm. It cannot be mapped on an XY axis. Clinical significance is the expert intuition of the bedside nurse, the physician, or the healthcare leader looking at the statistically verifiable data, acknowledging the practical magnitude, and asking the ultimate question: does this matter to the lived experience of this specific patient in this specific environment at this specific moment in time?
It requires synthesizing abstract math with profound human empathy.
Yes, exactly.
And maintaining that human empathy is becoming the central crisis of modern healthcare, which brings us to the frontier of this deep dive. Throughout this discussion, we have been looking at microscopic data sets, 3 hospital units, 6 diabetic patients, 100 midterm exams.
Small scale.
Right. But the final chapters of the Waxman text pull us aggressively into the reality of modern informatics, big data, and artificial intelligence. We are moving from spreadsheets you can scroll through to systems processing millions of data points every single second.
The transition from standard data analysis to big data isn't just about scale. It is a fundamental paradigm shift in how information behaves. The textbook frames this using the 6 V's.
Let's go through those.
The first is volume. We aren't talking about gigabytes anymore. We're talking about petabytes of continuous electronic health record data flowing from thousands of interconnected facilities.
The second is velocity, the speed of generation. A patient in the ICU isn't generating one blood pressure reading a shift. Their wearable telemetry is generating continuous, real-time physiological data streams that must be analyzed instantaneously.
The third is viscosity, which is fascinating in healthcare. Viscosity refers to the stickiness or complexity of the data. Healthcare data is highly viscous because it is rarely uniform. You have perfectly structured discrete data like a serum sodium level of 135 crashing into highly unstructured data like a 2-page narrative physician's note written in dense medical jargon.
Then you have variability. The data flows change depending on the season, the unit, or even the individual practitioner's habits. You have veracity, bringing us right back to garbage in, garbage out. How truthful and valid is the data being scraped from these systems?
Right.
And finally, volatility. How long is the data relevant? A patient's heart rate from 3 seconds ago might be highly relevant. Their heart rate from 3 years ago might be operational noise.
To process the 6 V's, human analysts are entirely insufficient. This is where predictive analytics and machine learning take over. The text outlines 2 primary branches of this artificial intelligence. The first is supervised machine learning.
And what does that mean exactly?
This is where human experts feed the algorithm massive amounts of historically labeled data. We show it 10,000 X-rays of healthy lungs and 10,000 X-rays of cancerous lungs. We train the algorithm on what to look for, and then we ask it to categorize new, unseen data based on those human-defined rules.
But unsupervised machine learning is where it gets both incredible and slightly terrifying.
Unsupervised learning involves taking a massive, chaotic lake of raw data and turning the algorithm loose without any labels, without any rules, and without any human preconceptions. The algorithm hunts for hidden mathematical structures, microscopic correlations, and phantom patterns that the human brain lacks the processing power to ever conceptualize.
These unsupervised algorithms power advanced alert monitoring systems. They can cross-reference a patient's subtle shift in respiratory rate, a minute drop in urine output, and a fractional change in a lab value, and accurately predict that the patient is going to crash into sepsis 6 hours before a human bedside nurse would ever notice the physical symptoms.
Exactly. It's incredibly powerful.
But let me challenge you on the philosophical core of this, because the textbook dedicates significant space to a very real debate. If a nurse leader is spending 12 hours a shift sequestered in an office, staring at a heat map of hospital variances on a monitor, or dictating patient care based on an unsupervised algorithm's dashboard dial, hasn't healthcare fundamentally lost its soul?
It's a fair question.
Are we turning the hospital into an automated factory floor where the patient is just an observation row in a massive database? Is being highly data-driven inherently antithetical to human caring?
It is the most vital tension in modern medicine. But the framework presented in the text argues passionately that the answer is no. It highlights Loxton's 2017 theory, technological competency, as caring and nursing. The core argument is that in a highly complex, infinitely dangerous environment like a modern hospital, mastering these digital tools is not a rejection of the human touch. It is the evolution of it.
Because you can't care for a patient if you can't see the unseen dangers threatening them.
Exactly. The infographic in the source material states that 96% of nurse leaders feel they have a deep moral duty to utilize their knowledge of data to help others. When a nurse leader understands the mechanics of standard deviation, when they can spot a truncated chart in a budget meeting, when they trust a predictive sepsis algorithm, they are not abandoning the patient for a machine.
Right.
They are utilizing a higher form of care. They are wielding mathematics as a shield. It's an act of profound systemic empathy translated through data.
So, what does this all mean? People often assume that staring at a spreadsheet turns you into a cold, calculating robot. But if you actually understand the language of data, the validity, the variance, the hidden correlations, that spreadsheet becomes something entirely different.
Very different.
It becomes a high-tech stethoscope. It allows you to place the earpieces in and listen to the physiological heartbeat of the entire hospital system. It lets you hear the quiet, statistical murmurs of vulnerability before the patient even knows they are in danger.
I think that is the most accurate way to frame it. Data fluency is no longer a niche optional skill for IT professionals or administrators. In an era of infinite information, data literacy is a strict moral imperative for anyone who wants to improve human lives.
What an incredible journey through the diagnostic muddy waters. We started by confronting the reality of garbage in, garbage out, recognizing that without rigorous reliability and validity, even perfectly collected data is a liability. We learned the absolute necessity of understanding our variables and respecting the rigid hierarchy of levels of measurement, a stark reminder that you can never, ever calculate the average of a room number.
We waded into the mechanics of descriptive statistics, unpacking the mathematical vulnerabilities of the mean and discovering why the median is the critical anchor we need when massive outliers threaten to distort our clinical reality.
Yeah, that 180 glucose spike.
Exactly. We moved past the deception of simple range and broke down the elegant math of variance and standard deviation, allowing us to accurately map the volatility of our systems.
We confronted the dark side of data storytelling, learning to spot the visual manipulations of impossible pie charts and the intentional panic induced by truncated y-axes. We mathematically quantify human behavior using Pearson's R and the complex contingency tables of the chi-square test, while permanently etching into our minds that correlation will never inherently prove causation.
Right, the phantom pattern problem.
And finally, we looked out over the horizon of big data and unsupervised machine learning, realizing that mastering these algorithms is the ultimate expression of technological caring. To you, the listener, the paradigm has shifted. The next time you are sitting in a boardroom or standing at a nurse's station and someone slides a beautifully designed dashboard or a massive Excel spreadsheet across the table, you aren't going to see an intimidating blur of digits anymore.
You'll see the story.
You are going to look straight through the numbers and hunt for the underlying story. You are going to immediately interrogate whether the data is actually valid for the decision being made. And you are, without fail, going to check if that y-axis actually starts at zero.
This raises an important question, though, as we move forward. As we feed more of our reality into these systems, and as unsupervised machine learning algorithms become capable of making incredibly accurate, life-altering clinical decisions at a speed we can scarcely comprehend, how will our definition of clinical significance have to evolve? When the algorithm finds a pattern of disease that is so complex, so deeply hidden in the 6 V's of big data that the human brain literally cannot conceptualize it, how do we keep that deeply human, expert intuition in the loop?
It's a daunting thought.
It is. How do we ensure that we continue to govern the math rather than letting the math govern the care?
That is the defining ethical and operational challenge of the next era of medicine. Thank you for taking this deep dive with us. We'll see you next time.